Introduction. Throughout the second half of the 20th century, two domains shaped global military and technological power more than any others: guided missile systems and nuclear technology. Both fields were led and significantly advanced by the United States. The AIM-7 Sparrow, a medium-range air-to-air missile, remained a backbone of U.S. aerial warfare capabilities for decades, while America's nuclear program transformed the balance of global power and gave birth to a massive civilian nuclear energy sector. This article explores both 1. The development, features, and historical relevance of the AIM-7 Sparrow, and 2. The rise of U.S. nuclear technology, including civilian nuclear energy and strategic influence. Part 1. The AIM-7 Sparrow Missile. 1.1 Origins and Development. The AIM-7 Sparrow was developed in the early 1950s when jet fighters and radar technology were evolving rapidly. Traditional machine gun dogfights were becoming outdated, and militaries needed weapons capable of engaging enemies at longer ranges. The U.S. Navy initiated the project to create a radar-guided missile that could be launched from fighter aircraft. Early versions entered service in the mid-1950s. Over the next 40 years, improved models were produced, making Sparrow one of the longest-serving medium-range air-to-air missiles in the world. 1.2 Technological Design, Non-Sensitive Overview. The Sparrow uses semi-active radar homing, meaning the launching aircraft illuminates the target using its radar. The missile's seeker detects the radar reflection from the enemy aircraft. The missile then guides itself toward that reflected signal. This type of guidance was revolutionary when Sparrow was introduced, providing significantly more accuracy than earlier infrared-guided missiles. It allowed pilots to engage targets beyond visual range, although still with important limitations compared to modern active radar missiles like the AIM-120M ROM. 1.3 General Characteristics. While detailed technical parameters are restricted for security reasons, the AIM-7 Sparrow can be described with open-source, non-sensitive characteristics. Role: medium-range air-to-air missile. Guidance: semi-active radar homing. Platforms: F-4 Phantom II, F-14 Tomcat, F-15 Eagle, F-16 Fighting Falcon, early variants F/A-18 Hornet. Warhead type: conventional, general-purpose fragmentation. Operational use: U.S. Air Force, U.S. Navy, and NATO allies. Its multiple versions, such as AIM-7E, AIM-7F, and AIM-7M, represent adjustments in electronics, propulsion, and reliability. 1.4 Combat use and historical importance. The Sparrow saw action in several major conflicts. Vietnam War. The AIM-7 was used extensively in aerial combat. Early limitations included reliability issues and the need for pilots to maintain radar lock throughout the missile's flight, which could be difficult in dynamic dogfights. Middle East conflicts. Various U.S. allies used Sparrow in several regional conflicts, contributing to its global legacy as a widely deployed NATO standard missile. Gulf War, 1991. The AIM-7M variant demonstrated significantly improved effectiveness. A large number of confirmed air-to-air kills in Operation Desert Storm were achieved using Sparrow, particularly by F-15 Eagles. Because of its availability, reliability, and range, Sparrow played a central role in achieving air superiority. 1.5 Evolution toward modern missiles. Beginning in the late 1980s and early 1990s, Sparrow began to be replaced by the AIM-120M ROM, which had several advantages. Active radar guidance, fire-and-forget capability. Better performance against maneuvering targets. Improved reliability and electronics. Nevertheless, Sparrow's importance in shaping American and NATO aerial warfare doctrine is undeniable. It served as the technological foundation for future missile systems. Part 2. American Nuclear Power and Technology. 2.1 Introduction to the U.S. Nuclear Program. The United States launched the world into the nuclear age with the Manhattan Project during World War II. While the military aspects of nuclear technology are strictly classified, the broader development of U.S. nuclear science has profoundly influenced energy production, medical advancements, space exploration, scientific research, global strategic power. This section focuses on open, civilian level, and historical aspects of U.S. nuclear technology. 2.2 Civilian nuclear energy in the U.S. After World War II, the U.S. promoted atoms for peace, encouraging the peaceful use of nuclear technology. In 1951, the first experimental reactor produced usable electricity. Over the next decades, dozens of nuclear power plants were built. Nuclear energy became a major component of the U.S. electrical grid. Today, the U.S. operates more nuclear reactors than any other country. On average, nuclear power generates about 18–20% of all U.S. electricity. 2.3 Why nuclear power matters. Low carbon emissions. Nuclear plants produce massive amounts of electricity with near-zero greenhouse gas emissions, making them essential for fighting climate change. High reliability. Nuclear reactors run reliably for long periods without interruption. Their capacity factor is higher than solar, wind, or even fossil fuels. Energy security. Domestic nuclear plants reduce dependence on imported fossil fuels. Technological leadership. The U.S. leads in nuclear research, reactor safety, uranium fuel technologies, and reactor designs. 2.4 U.S. Nuclear reactor types. The United States primarily uses pressurized water reactors (PWRs), boiling water reactors (BWRs). Both are considered highly safe and well-regulated technologies. New advanced designs are under development, such as small modular reactors (SMRs), advanced generation IV reactors. These aim for higher efficiency, better safety systems, and reduced waste. 2.5 Nuclear technology beyond electricity. American nuclear science extends to many areas. Medical use. Cancer treatment, radiation therapy, diagnostic imaging, PET scans, CT scans, production of vital medical isotopes, industrial and research use, materials testing, agriculture and food sterilization, scientific particle research reactors, space exploration. NASA uses radioisotope thermoelectric generators, RTGs, a type of nuclear battery, for missions to distant planets where solar power is insufficient. Examples include Voyager 1 and 2, Cassini spacecraft, Curiosity and Perseverance Mars rovers. 2.6 Global political impact of U.S. nuclear technology. Nuclear technology dramatically changed geopolitical dynamics. The U.S. became one of the world's leading nuclear powers, established global non-proliferation frameworks, led international nuclear safety standards, played a major role in organizations like the IAEA, International Atomic Energy Agency. U.S. nuclear policy focuses on preventing the spread of nuclear weapons while supporting peaceful nuclear energy programs worldwide. Part 3. Intersection of missile and nuclear technologies. Although the AIM-7 Sparrow itself is a conventional air-to-air missile and not related to nuclear weapons, both missile development and nuclear technology represent sophisticated branches of American defense and scientific research. Common themes include advanced electronics, high-level engineering, strategic impact on global security, continuous modernization. Missiles like the Sparrow help the U.S. dominate air superiority, while nuclear technology shaped global strategy and civilian energy systems. Conclusion. The AIM-7 Sparrow missile stands as one of the most influential weapons in the history of American air combat, marking a major transition from visual-range dogfighting to radar-guided engagement. Its decades of service across multiple wars highlight the technological innovation and operational reliability of U.S. missile systems. Similarly, American nuclear technology, spanning from power generation to medicine and space exploration, has reshaped modern civilization. The U.S. remains a pioneer in nuclear science, safety, and international policy.